Hello, advanced geometry students. It's Mr. Donaldson. I had a little notes video here over sections 2.1 and 2.2, and I do apologize for the little bit of echo that you can hear in this room. Today's lesson focuses on inductive reasoning. You all, inductive reasoning is nothing special or new. It's something that you've been using your entire life. Every time you touched a hot stove and your finger burnt and you realize, hey, I shouldn't touch that hot stove, you're really just using inductive reasoning. So inductive reasoning is a process of observing data, recognizing a pattern, and making a generalization about the pattern that you recognize. So a good example of that would be like observing data. Each day when you've come into my class, you've observed that I've been playing music. Then you recognize a pattern. You say, hey, you know what? It seems like every day I go in there, he's playing music. There's a pattern there. Every day he's playing music. And then you make a generalization. And that generalization would be, you know what? I'll bet he's going to be playing music tomorrow. That is inductive reasoning at its finest. It's not guaranteed to work. Of course, you come in tomorrow, I could be like, no, I stopped doing it. I'm not going to, but I could. A conjecture is that generalization that you make. So for you all, when you first observe the data of, hey, he played music. Hey, he played music. Hey, he played music. You recognize the pattern. You know what? He plays music every single day. And then you're making a conjecture. You probably tell your friend or whoever, like, hey, Mr. Donaldson's going to play music tomorrow. And that's you're making a conjecture based off your ability to use inductive reasoning. We use inductive reasoning in math all the time. And the simplest way we do that is by just being able to observe a sequence of numbers and determine what you think would come next. So in this first sequence, you'll notice that there's a pattern. And hopefully you see that that pattern is you're simply going up by 4 each time. I go up by 4, I go up by 4, I go up by 4. So, first you observe the data. There's a 1, there's a 5, there's a 9, there's a 13. Then you recognize the pattern. Hey, it's going up by 4 each time. And now I'll make a conjecture. My conjecture is, you know what? The next number of the sequence will simply be the previous number plus 4. When I add 4 to 13, I get 17. And then when I do that again, I get 21. That is inductive reasoning, and it's as simple as that. So sometimes it takes a little more work to find the pattern. So in this next example, the first thing that I would notice based on what we did for example 1 is I'd probably be like, hey, he's adding 3 each time. But when you look at this next number difference, I'm not adding 3, right? In fact, I took away 6. And then you get this next number, you're like, oh man, now he's what, adding 12? I don't know what's going on. But you're not limited to addition or subtraction. There are other operations as well. And so another operation to consider is multiplication or division. In fact, I noticed that 1 and then 2 and then 4 and then 8, those are just numbers that are being doubled. And then the alternating negative signs indicate you'd probably be multiplying by a negative number. In fact, check it out. If I multiply by negative 2, negative 1 times negative 2 is a positive 2. And if I multiply by negative 2 again, negative 2 times negative 2, positive 2 times negative 2 is a negative 4. And when I multiply by negative 2 again, negative 4 times negative 2 is a positive 8. So in this case, the pattern that I recognize is, hey, I'm multiplying by negative 2 each time. And if I continue that by using that as a conjecture, hey, I'm going to continue this pattern by multiplying by negative 2 each time, the next number will be negative 16 and then 32. Now example 3, this is gnarly. This is really hard. You probably have like one of these on an assessment, all right, just to see who gets 100 or not. But what you're going to do differently in this specific example is you're going to pay attention to the fact that, hey, some of those numbers are fractions and others are not. And the nice thing about a fraction is that you can have equivalent fractions. So, for instance, 3 is not simply 3 over 1. It could also be 6 over 2 or 9 over 3 or 12 over 4. So you have some freedom to manipulate these fractions until you see a pattern. Because right now, the pattern is not evident. So what I'm going to do is I'm going to rewrite all of these as fractions. Now, of course, 5/3 is given to me. And I'm not sure what fraction you use for 1 yet. 3/5 is given to me. And then 1/3 is given to me. And then, of course, here are the 2 ones that I don't know. So what I've got here is I'm thinking, all right, I can look at the numerator, and it looks to me like the numerators are decreasing. So that's helpful. And then I look at the denominator, and I see that the denominator, well, is increasing at first, but then this 1/3 is kind of throwing me off. And what I see right away is that a nice pattern that would be great is if this was a 6 and a 5 and a 4 and a 3 and a 2, and if this were a 2, a 3, a 4, a 5, and a 6. And I can totally make that happen by making this 3, instead of being 3 over 1, I'm going to make it 6 over 2. Instead of this 1 being 1 over 1, if I want this pattern to work, man, it would be great if there was a 4 on top, 6, 5, 4, 3. It'd be great if there was a 4 on bottom, 2, 3, 4, 5. And 4 over 4 is 1. Now the problem here with this pattern, though, is that this 1/3 is throwing me off. But again, 1/3 is not the only fraction that would be equivalent to that. 2/6 also works. And now I've found a pattern that works. On the top, I'm decreasing by 1 each time in the numerator there, and on the denominator, I'm increasing by 1 each time, which leads the next one to be 1/7, and then the following term to be 0.8. So to fill in my blank here, this would be 1/7, and 0 divided by 8 is simply 0. Now we can also use inductive reasoning with figures, and that's what we have here. And this is really straightforward and easy. We've got a triangle, 3 sides, quadrilateral, 4 sides, pentagon, 5 sides, hexagon, 6 sides. So all I need to do here is just to create a heptagon, or a 7-sided polygon. I'm going to do my best here and hope I don't screw it up. Was that 4 sides? 5, 6, 7. There we go. A heptagon would be the next figure. Now, sometimes when we're doing these types of inductive reasoning problems, it would be really helpful, especially if I ask you for some term way down the sequence, to come up with what's called a function rule. And that's what we're going to do now. And the reason it would be helpful is if we go back and look again at example 1 here, I know pretty easily what the 4th term is. It was 17. And I can figure out what the 5th term was by adding 4 again to get to 21. But suppose I gave you this sequence and said, hey, what's the 30th term here? Well, adding 4 30 times would be a bit tedious and kind of a pain in the butt. So there's a little trick we learned, and that is called writing a function rule. A function rule gives the nth term or a specific term of a sequence. So, for instance, if I wanted to know, in this case, like the 23rd term of a sequence, I'm trying to write some formula or rule where you simply plug 23 in, and it spits out the correct term for that. So, when you're doing this, the very first tip I'd say is first look for constant differences. If you have a constant difference, that's going to be your coefficient for n, or the value or the variable that you're going to plug in for. All right? So first, let's take a look at that, and then I'll show you an easy way to think about it as well. So what I notice is here's the first term, the second term, the third term, the 4th term, and so on. And the first term is 1. The second term is 5. So initially, what I observe is I believe it's going up by 4. And then I'm going to confirm that. Look, from the second to third term, I add 4 again, from 5 to 9. From the third to the 4th term, I add 4 again. So what I'm observing is that this sequence is simply adding 4 each time. Now, notice I'm not just asking you for the 5th term, because if I were, you would just put a 17 in there. What I want you to do is to come up with a function rule, some rule or formula that will let me find any term in general, and we'll call that term the nth term. If I go back to my little tip here, if there's a constant difference, which there is, that's going to be a coefficient for the variable n. And the coefficient is a number you multiply it by. So what I posit is my rule, my function rule, will look like this. 4n, but then plus or minus something. So let's take a look at what I have if I simply just do 4 times n. Well, if I plug in 1, 4 times 1 is 4. If I plug in 2, 4 times 2 is 8. If I plug in 3, 4 times 3 is 12. 4 times 4 is 16. But you'll notice 4 is not 1. 8 is not 5. 12 is not 9. And 16 is not 13. So this rule is not working right now. But I can make a slight adjustment. When I plugged into this 4n rule, every time I got a number that was 3 bigger than the actual term. 8's 3 bigger than 5, 12's 3 bigger than 9, 16's 3 bigger than 13. So I can simply fix that by subtracting 3. So my rule is just 4n minus 3. And now if I want to know the 23rd term, I can just plug in 23. But before I do that, I'm just going to confirm that this works. All right? So if I plug in 1, 4 times 1 is 4, minus 3 is 1. When I plug in 2, 4 times 2 is 8, minus 3 is 5. When I plug in 3, 4 times 3 is 12, minus 3 is 9. And when I plug in 4, 4 times 4 is 16, minus 3 is 13. These are all working. So if I want to find the 23rd term, or in function notation, the function or f of 23, I would simply do 4 times 23 minus 3, and what I end up with is 89. Now you'll notice that this looks a lot like this. And if you remember linear equations from Algebra 1, this would be a pretty easy idea for you to grasp. Slope is the constant difference. Well, 4 was my constant difference. But the other thing that may be helpful for this is that understanding that b is the y-intercept. And the y-intercept is the 0 term. It's where the graph crosses the y-axis. So when the input or the x value is 0. Well, if I come back over here and I think about, well, what would the 0 term have been? Well, really, I'm just adding 4 each time. So I could subtract 4 from this first number, which is 1, which would give me negative 3. So an easy way to find this part of my formula is to simply determine the 0 term. And in this case, that was negative 3. So for the next example, I'll show you how we can do that quickly. All right. So here, in this case, I'm just going to do that same process, but I'm going to do it faster. I'll show you. So check it out. First I notice is, oh man, it's going down 5. It's going down 5. It's going down 5. So right then and there, I know it's going to be negative 5n. But if I just multiply 1 by negative 5, I don't get 2. I get negative 5. There must be something I add or subtract to this to make it work. And the fast and easy way to do it is just go backwards one and think, what would the 0 term have been? So, what number would I have subtracted 5 from to get 2? Well, I'll simply go backwards and I'll add 5 to 2 to get 7. And so I see that the y-intercept, or the number we need to add or subtract here at the end, is a positive 7. And I'm just going to make sure that works. Negative 5 times 1 is negative 5, plus 7 is 2. Negative 5 times 2 is negative 10, plus 7 is negative 3. Negative 5 times 3 is negative 15, plus 7 is negative 8. This is panning out. This is working. And then if I want the 23rd term in this sequence, I'll simply plug in 23 to my formula, and it spits out negative 108. Will be the 23rd term in this sequence. All right, you on the last example, and we're not going to get to the factoring today, and that's okay. But this last example, you'll notice that this is a little bit different. In this case, you're adding 3, but then you're adding 5, but then you're adding 7. So what's happening is that it's not a constant difference. This is not linear growth. This must be some sort of exponential growth. And so when it's exponential growth like this, when the difference is increasing, you should try a squared or a cubic or some other sort of exponential function that will work. So what I'm going to try is n squared and see what I get. So if I square 1, I get 1. If I square 2, I get 4. If I square 3, I get 9. If I square 4, I get 16. Well, look, 1 is not 4. And 4 is not 7. And 9 is not 12. And 16 is not 19. But if I simply add 3 to 1, I do get 4. If I add 3 to 4, I do get 7. If I add 3 to 9, I get 12. And if I add 3 to 16, I get 19. So squaring it got me close, but then all I had to do was add 3 to fix it. So to get this 23rd term of the sequence, I'll simply plug in and do 23 squared plus 3, and that spits out 532. So I realize that there are some factoring problems on this note sheet, but I think that's adequate for today. You can go ahead and start your assignment, and thank you so much for paying attention. I hope you have a wonderful day.